Group 5, and our topic is Introduction to Braking System. Introduction. A braking system is a safety mechanism used in vehicles to slow down or stop movement by converting kinetic energy into heat through friction. It helps drivers maintain control of the vehicle, reduce speed when necessary, and ensure safe operation on the road. Modern vehicles use various braking systems, such as disc brakes, drum brakes, and anti-lock braking systems, ABS, to improve braking performance and safety. Major components: ABS control module, reads data from the speed sensors and prevents wheel locking during emergency brake. Brake booster, uses engine vacuum or an electric pump to multiply the force from your foot, making it much easier to press the pedal and stop the car. Brake pedal, when pressed, it mechanically initiates the braking force by pushing fluid through the system. Disc brake, slows the front wheels by using a caliper to squeeze high-friction brake pads against rotor. Drum brake, slows the rear wheels by forcing curved brake shoes outward against the inside of a spinning metal drum. Emergency brake lever, mechanical backup system that bypasses the hydraulics to lock the rear wheels and keep the vehicle parked. Wheel speed sensor, continuously monitors how fast a wheel is spinning and sends this data to the car's computer to detect if a wheel is locking up.
Welcome to Bendix Brakes. Today we'll look at how a modern disc brake system works. We'll start by looking at the brake components involved in stopping a vehicle and how they work together. Starting with one of the main components in the braking system, we look at the disc rotor, which the brake pads squeeze against. This will create friction that decelerates the rotation of the wheel and the vehicle. The caliper is activated by the brake fluid hydraulic pressure produced from the vehicle's brake pedal and master cylinder. In this assembly, the brake pads are squeezed up against the disc rotor surface to create friction. A caliper is made up of multiple parts, all critical in the effective operation of the brake system. These parts include the caliper and mounting bracket, slide pins, locking bolts, dust boots, brake mounting clips, brake pads and shims, the brake piston with the dust boot and seal. The caliper is fed brake fluid through a banjo fitting, which drives the piston forward towards the inside brake pad when the brake pedal is pushed. This causes the caliper to move along the slide pins, which then pulls the outside brake pad up against the brake disc rotor. Now that we understand the parts, let's see how the braking system works. Hydraulic brake pressure will cause the caliper to move along the slide pins, pulling the outer brake pad against the opposite side of the disc rotor, causing friction and decelerating the brake and the vehicle. When the brake pedal is pressed, the caliper will receive high-pressure brake fluid from the master cylinder, which will push the piston into the inside brake pad and onto the disc rotor surface. Looking at the braking process from another angle, we can see the brake fluid pushing the piston, which in turn pushes the inner brake pad against the inside of the disc rotor. Once this has happened, the fluid will now push the caliper along the slides and the outer brake pad will be pulled towards the opposite side of the disc rotor. Thanks for tuning in. We hope you've learned the fundamentals of how Bendix brake pads work with a modern braking system. And always remember to fit Bendix brakes.
Anti-lock braking system, ABS, is an automated safety feature that prevents cars' wheels from locking up and skidding during hard braking. Electronic sensors detect if a wheel is about to stop spinning and instantly pulse the brake pressure to that wheel dozens of times per second. This rapid pumping action keeps the tires rolling just enough to maintain grip, allowing safe steer around obstacles while slowing down.
This section examines the anti-lock braking system. Applying brakes too hard or on a slippery surface can cause the wheels to lock. When wheels lock, steering control is lost and, in most cases, it produces longer stopping distances. The anti-lock braking system prevents wheels locking or skidding no matter how hard brakes are applied or how slippery the road surface. Steering stays under control and stopping distances are generally reduced. It consists of a brake pedal, a master cylinder, wheel speed sensors, the electronic control unit or ECU, and the hydraulic control unit, also called a hydraulic modulator. The wheel speed sensor consists of a notched or toothed rotor that rotates with each wheel and a pickup. As the wheel turns, a small voltage pulse is induced into the pickup and sent to the electronic control unit. When the brakes are applied, the wheel's speed of rotation changes. This sends a new signal to the ECU. If the control unit detects that a wheel might lock, it sends a signal to the hydraulic control unit. In a 3-channel system, the hydraulic control unit uses 3 solenoid valves to control brake pressure and prevent them locking. The valves are in series with the brake master cylinder and the brake circuits. One operates for each of the front wheels and one controls both rear wheels. At the start of a journey, the ABS automatically checks itself. Any failure in the system lights up a warning light in the dash panel.
Hello everyone, welcome to this presentation on braking physics and hardware calculations. Today, we will explore the engineering behind how a vehicle stops, moving from the macroscopic vehicle dynamics down to the mechanical forces inside the brake caliper, and finally, the ultimate limits of road adhesion. Let's dive into the core physics. First, let's look at the vehicle dynamics perspective. This method calculates the total linear force required to decelerate or stop a vehicle based on Newton's second law of motion. The total braking force, F flat, equals mass times deceleration, plus any opposing road forces like aerodynamic drag and rolling resistance. However, during high deceleration emergency stops, these road forces are so small compared to the tire braking force that we can neglect them. Therefore, the formula simplifies to F flat is approximately equal to mass times deceleration. Let's apply this to a real-world scenario. A mid-sized vehicle with a mass of 1,650 kilograms is decelerating at a steady rate of 7.5 meters per second squared. Assuming road resistance is neglected, what is the required braking force? By looking at the bright formula on the screen, we multiply 1,650 kilograms by 7.5 meters per second squared. The math gives us a total required linear braking force of 12,375 newtons, or approximately 12.38 kilonewtons. Now, let's transition to the mechanical perspective. How is that linear force actually generated by the brake hardware? To find out, we must work backwards from the tire to the caliper. Step 1 is calculating the brake torque, TB. The braking force at the road is created by a torque resisting the wheel's rotation, which is TB equals braking force times the effective radius of the tire. Step 2 is finding the caliper clamping force, F clamp. This torque is generated by the friction between the brake pads and the spinning rotor. Rearranging the formula, we get F clamp equals brake torque, divided by 2, times the friction coefficient, times the rotor radius. The factor of 2 accounts for the brake pads gripping both sides of the rotor. Let's look at the engineering design for a sport sedan. A single front wheel must generate a braking force of 4,000 newtons. Given a tire radius of 0.3 meters, a rotor radius of 0.15 meters, and a pad friction coefficient of 0.4. First, the brake torque. As highlighted in yellow, 4,000 newtons times 0.3 meters gives us a required brake torque of 1,200 newton meters. Next, the clamping force. We take that 1,200 Newton meters of torque and divide it by the product of 2 times the friction coefficient of 0.4 times the rotor radius of 0.15 meters. This calculation reveals that the caliper pistons must exert a massive clamping force of 10,000 newtons, or 10 kilonewtons, to stop the wheel. In braking system there are calculation to see the maximum braking force. It means the maximum brake that can be applied without the wheel sliding. The element that affected are two main subject, which is the coefficient of friction and the vertical load or N value. When the braking force exceed the value, the tire will lose the grip and start to skid. This will affect the handling of the car and braking power. Next is the formula for the maximum braking force consists of F flat, max, which is the maximum braking force, U or mule is the friction coefficient between the tire and the road surface, and lastly the normal forces or vertical load acting on the brake. Sample question: a vehicle with the total mass of 1,500 kg is traveling on a flat and dry asphalt road. The average coefficient of friction mule between the tire and the dry asphalt is 0.8. Assuming the braking system distributes force perfectly across all wheel and ignoring aerodynamics drag. Calculate the total maximum braking forces the vehicle can generate before skidding. From the question we take out the parameter, which is mule is 0.8, mass is 1,500 kilograms and gravity acceleration is 9.81 meters per second square. From that we need to find the N force by multiplying mass with gravity acceleration and get able to get 14,715 Newton. Then we calculate the maximum braking force by multiplying mule or coefficient of friction and N force, and the answer is 11,772 Newton for maximum braking forces. With this answer we able to know the value of maximum braking forces is 11,772 Newton before is sliding on the road. In conclusion, we able to know how to braking system and calculation for braking force and the maximum braking force. The application of the calculation so it prevent the vehicle from skid on the road is important to know.